Okay, here's a video showing you the solution to problem 7.1 from Stallings. This is part of homework 4 this semester. We have a data rate of 56 kilobits per second, and we're looking at spread spectrum, and so we're looking at very low signal-to-noise ratios, 0.1, 0.01, 0.001. And just think about what this means. 0.001 means that the signal is 1/1000th as strong as the noise. How can that be? Well, it can be as long as you have large bandwidth, okay? And that's the idea of spread spectrum, is you can have poor signal-to-noise ratio, but if you trade off with bandwidth, then you can have effective communication. So Shannon's equation shows that trade-off. You have bandwidth here and you have SNR here. The thing to remember about Shannon's equation is that the SNR is not given as a decibel value. It's given as a ratio. And so what we're going to do is we're simply going to take this data rate and set that equal to the channel capacity. We're going to set the SNR to the various values, and we're going to solve for the bandwidth. So the B is C over log 2(1) plus SNR, and we can do the calculation very simply, just plugging in. And you'll notice that as we get smaller and smaller signal-to-noise ratios, then we need more and more bandwidth in order to send that 56 kilobit per second signal. And so it ranges from 400 kilohertz to 4 megahertz to 40 megahertz roughly. So very small signal-to-noise ratios require lots of bandwidth. Conversely, if you have lots of bandwidth and you spread out your signal, you can live with very small signal-to-noise ratios. That's the idea here. Okay, for part B, we go to a signal-to-noise ratio of 1. We go to a bandwidth efficiency of 1. Spectral efficiency is what we've called this. Okay, spectral efficiency, data rate divided by bandwidth, 1 bit per second per hertz. Let's use that as our spectral efficiency, and those are two of the quantities that appear in Shannon's equation. And so we can calculate the signal-to-noise ratio that's required for a spectral efficiency of 1. And when we solve for the signal-to-noise ratio in Shannon's equation, we get this, 2 to the C over B. Well, C is our data rate, C is our channel capacity, 2 to the 1 over 1 minus 1 is 1. And so so for a signal-to-noise ratio of 1, we only need 1 hertz for every bit per second that we're sending. Whereas here, for the very small signal-to-noise ratios in part A, even for a small data rate of 56 kilobit per second, we needed much wider bandwidth, much higher than 56 kilohertz, for example. And so the idea here is that this is an illustration of Shannon's equation and its relation to spread spectrum. Hope that helps.